Alright, so this is going to be the part 7 of the lecture 4. So we actually talk about the many definitions up to this point. So I think we're in a position of actually how you use them. So we actually talk about the work being the negative pressure multiplied by the change in volume. But when the reaction is done in a closed container, like in the some closed containers, then change in volume is 0, right? Because everything is contained inside of the closed container, so you can't really change the volume. In that case, this value right here, remember that delta U, the change in internal energies, is equal to heat plus the work. We can't do anything about the heat, but we actually substitute the work with the minus P multiplied by the change in volume. But change in volume is 0. Anything multiplied by 0 is actually 0. So this term is going to go away. So basically, delta U is equal to just heat, right? So specifically at the constant volume. So we're going to put the subscript B denoting for the constant volume. So the heat at constant volume is equal to the change in internal energies. This is not as useful as the next one, but it's still you can actually get a good value of this guy by using some sort of an instrument that we are going to talk about. So not this particular videos, but next one. So hold on to that one. The more important one is actually called the reactions carried out at constant pressure. So this one right here is not the constant volume, it's a constant pressure. So for this one right here, the reaction is actually happening in the open container, like for example reactions inside of the beaker, right? Those are the constant pressure, and everything that's happening in our body is actually a constant pressure too, right? Because we live in the 1 atm conditions, so anything that happens in our body is actually pressure is constant. No matter the volume change or not, it really doesn't matter. It's the constant pressure, right? So again, I'm gonna write this delta U is equal to Q plus W. That's the changing internal energy is equal to heat plus work, and QP denoting the heat at constant pressure. And then I'm going to substitute this W with minus P delta V, and then rearrange these equations, that and this, for the QP. Then you get delta U plus P delta V, right? So notice that the QB, the heat at constant volume, is different from the heat at constant pressure. So by the different process, the value of the heat is going to be different. So you have to be very careful with, is this a constant volume process or the constant pressure process? You always have to ask about that one. I think I actually talked about this one. The QB is everything is done in fixed size box, the closed container. QP is a fixed pressure, open air, right? So we actually going to talk about this QB in the next videos, but for the QP we didn't really talk about that one, right? So I'm gonna actually talk about the QP first. Before I actually talk about QP, let's just define the enthalpy H, and this is another state functions, and that's equal to energy plus pressure times volume. This is a definition. The reason why I actually think this is useful is because the change oops, let me just try to like this. So the changing H can be actually comes from the changing internal energies plus change in pressure times the volume, right? So at constant pressure, the constant pressure, that pressure doesn't change, right? So the pressure being constant, delta U plus P delta V. So far it doesn't look so appealing, but let's just substitute delta U with the stuff that we had before. It's not in here. Where was I? So the delta U is actually Q plus W, right? But W is what? That's constant pressure process, right? And that one right there is a minus P delta V, right? W is always equal to minus P delta V. And P delta V, so these guys actually cancel off. And then this becomes QP. So QP is now the same thing as the delta H. So delta H is the value for the QP. And this delta H being state functions, so the delta H is actually equal to the enthalpy of the product minus enthalpy of the reactant. So if I actually have the table of the enthalpy values of the product and the reactant, then actually I can actually calculate the delta H for the reactions too. And remember that delta H is a heat too, right? So if the delta H value is positive, we can say that's endothermic process. And then if the delta H is negative, that's exothermic process. The heat is actually going out of the system. So right now we don't really talk about this enthalpy that much, but let me just try to maybe the next slide may actually have a little bit more information. So the reason why that we actually care so much about this delta H is that we can actually make a table, and typically that the textbook generally have like quite a bit of the delta H values for the many of the chemicals too. It's actually called the enthalpy of the formations, but I'm not completely sure I'm going to talk about the enthalpy of formation in this particular videos, but we're going to talk about that one in the quizzes. So the let's just think about the particular process of the water actually going from the solid to liquid. So the ice is melting to the liquid. That process is an endothermic process. The heat is actually positive, right? Remember that this one right here, if the delta H is positive, it's an endothermic process, right? Positive value means that the heat is going inward, right? So it's kind of funny that if you actually see the snows outside, that actually snow, the formation of snow is actually is a good thing, because that snow melting to become a liquid, actually the actually the other way around, it's the liquid turning into the snow. That process is actually an endothermic process, right? So the heat is going in to the snow, right? And if the other way around, the liquid is now turning into solid, then that's an exothermic process. So if the liquid is turning into solid, this value actually becomes negative right here because it's going the other way around. Maybe I shouldn't have actually talked about that one, not right now, but yeah, it's okay. If the solid ice becoming liquid, it absorbs heat, and then on the other directions, then that H2O liquid, let me just try to write out the entire process now. H2O liquid going into the H2O of solid. This process, delta H, is actually negative 6.01 kilojoule per mole. The reason why I know that is because let's just try to add these two reactions. What happens here? If I add all of these guys like this, then the liquid sorry, liquid and the liquid cancel, the solid and solid cancel, so there's nothing become nothing, right? That's a no process, meaning that it's zero, right? And we know that the the second process right here is actually the negative 6, right? A positive 6, sorry. This process is actually a positive 6. That means that this process right here has to be negative 6. Because if you add these things up, then it has to add up to 0, right? So by that, this one right here is actually supposed to be negative. So anytime that you actually swap the product and the reactant, this becomes actually negative. Negative of the forward process. So if this case right here is a positive, then going the other way around, there's a H2O liquid is becoming the H2O solid, then this process is becoming negative because it's going the other way around. Okay, I think I might have actually talked about something that I'm supposed to talk about it in the next few slides, so I'm gonna stop right here. Alright, then let's talk about this one right here. This one right here is a combustion, right? Combustion of methane gas with the oxygen to produce carbon dioxide, and then the liquid water, right? Delta H value, this one right here is negative. That means that heat is released outward from the system, which is the methane for this particular case, methane and oxygen, right? So that releases the heat. This one that releasing the heat is actually the stuff that we see from the fire, right? It's the methane combustion that heats up the room, right? So that was that. And I started to mention about this manipulation of the delta H values. Then three stuff that you should probably remember is that you always specify the state of the reactant and product. That's important. And then that if you want to multiply the whole equations, then you can multiply the whole equations. But also you have to multiply the delta H value that's associated with that particular chemical reactions. And reversing an equation should change the sign of the delta H, but not the magnitude. So let me just try to go through several stuff here. So the given reaction right here, this means that 1 mole of the C6H12O6, that's sugar, right? Glucose, reacting with the oxygen to produce CO2 and then H2O, right? That's 1 mole. And 1 mole is like 180 grams, right? But what if you are interested in only like a 45 gram of the glucose, not the entire 1 mole, but just part of it? Then you just need to multiply this value right here with the part of the whole molecule. So that's the heat that comes out of the burning the only 45 gram of the glucose, not the 180 like this one right here. You are burning 180 gram because the molecular weight is 180 gram, and then this is one, right? I think we actually talked about this one at the very first exam portion of it, so I'm gonna skip over this. I may actually have talked about this one in the first exam again on the very first couple of quizzes. So the Hess's law, it just stated that you can add the many chemical reactions. So for example, if I'm interested in this particular reactions, the delta H value for this particular reactions, but I only have the information for these guys, then what do I do to actually get the delta H value for this particular reactions? Looks like that I can add these two reactions to make this one, right? The C and C is gonna cancel, and then A and B becoming D, right? So I simply added these two reactions, right? Then for the delta H value, you do exactly the same thing. Since you simply added these two equations, you can just add the delta H reaction for these two reactions to get the delta H value for the A and B becoming D. Alright, so this is the exercise, so you can probably pause this video and then you can actually try to work these things out. What I want is the delta H value right here for this particular reactions, but you're given these informations. So good luck, and then do that, and then come back to this video. The way to do that, by the way, is that realizing that this one right here shows up on the reactant side, and then this one right here shows up on the product side. So maybe that you might need to swap the product and reactant here on the second one. The first one you don't probably need to do anything. And do you need to multiply any one of these things? Alright, so let me just go to the next one. So you have already worked out the situation, so I'm just gonna cover what's supposed to happen. So this one right here, I'm just gonna use straight out 2Al and then the O2 reacting to produce Al2O3. So there's no change, right? And delta H value for that is actually this guy right here. The second reaction, because Fe was actually shows up on the product side of the target equations, right? That was on a target, so I'm gonna have to swap these guys into the product and then these guys into the reactant, right? So that's what I did, and when you do, you're gonna have to change the positive negative. So if this was a negative 822, then the one that's being swapped becomes positive because it used to be negative, right? Then you're gonna add these things up. When you do add up these things, then oxygen it's gonna cancel, so you have this reactant and the product, the leftover stuff shows up here. Then you just simply added these two equations, right? So you're gonna add these guys. Then you actually get the delta H of that value right here. Let's do one more. The combustion of methane gas. But now that we actually want to have the H2O gas as a product. When you combust CH4 with oxygen, it used to be the water, right? If I actually go back all the way, then this reaction, it used to be the water, right? So I'm gonna use this equation and then that equation to make this thing looks like a gas here. So how do I do that? So this one right here, no change, right? And then you have this 2H2O is actually showing up on the product side. Now you're gonna have to cancel this 2H2O with the left hand side, and then you want to have the 2H2O gas instead, right? So what do I do for the where did it go? What do I do with this guy right here? I'm gonna put these things into the reactant, and I'm gonna put this, oh, not that one, but it's the gas, right? So if I actually have another equations, that's the well, actually it wasn't really a good one, so it's supposed to be the gas. So the gas and the liquid is different, right? So the liquid becoming gas actually absorbs the heat by that much. So you're gonna simply add these two. Sorry, so I was completely wrong about that one. We don't really use some these equations because this was the solid to liquid conversions, right? We don't use the solid and the liquid conversions. We use the liquid and gas conversions. So liquid to liquid cancel, then you want the gas. So if you use the table, you probably either have some H2O liquid becoming H2O gas, and that's probably kilojoule per mole. That's what you probably find for this one. Or either that, or you may actually find H2O of the gas is becoming H2O of the liquid. That's negative 44 kilojoule per mole. So you're gonna find in the textbook either this or that, depends on the textbook. So if your textbook is having this one right here, you're gonna swap the product and reactant and then put the negative values on the negative 44, right? That becomes 44, which is this one. And then to cancel out this 2H2O, you're gonna have to multiply everything. So multiply by 2, multiply by 2, and then so does this guy too, multiply by 2. Then you get this 88. And then you add these two, all of these guys. Then the left hand side, the leftover is this, and then right hand side, leftover is this and that. And then you just add these guys to get this one. So you just need to practice solving these type of problems.